In the last lesson of section 2.5, we will compare z-scores from two data sets, but this time we will only be given those data sets. We won't be given the mean and standard deviation of them. We'll have to find them. So before we do that, let's take a look at the introduction problem. So through our activity earlier in the year, we saw the average amount of time that someone waited for their food at McDonald's was 183 seconds with a standard deviation of 25 seconds. Right? I'm going to highlight that information. So at McDonald's, looks like we have a mean of 183 and a standard deviation of 25. So at Wendy's, the average wait was 112 seconds with a standard deviation of 15 seconds. Right? So at Wendy's, the average wait was 112 seconds and standard deviation of 15 seconds. So at a busy dinner time, you want a salad from Wendy's, but you also want a milkshake from McDonald's. So you go to both stores. You waited 131 seconds at Wendy's and 198 seconds at McDonald's. Even though you waited a minute longer at McDonald's, were these times expected? And it asks us to calculate the z-scores for the wait times and use them to justify our answer. Right, so it looks like here are our values that we want to use. Right, and just like in the last section, I think it's easy to organize our data into a table. So I'll have McDonald's, we have a mean of 183 and a standard deviation of 25 with our data value, or our wait time of 193 seconds. Then at Wendy's, right, we had a mean of 112 seconds, a standard deviation of 15 seconds, and our wait was 131 seconds. So we want to find the z-score of each of these. So for McDonald's, let's see, we will take 198 minus 183 divided by 25. Right, so our z-score there is 1.36. And at Wendy's, right, write down our z-score formula again. So we have 131 minus 112, all divided by 15. And our z-score is 1.27. Right, so to conclude this problem, both waits were longer than average, but they were both still usual waits since they were within two standard deviations of the mean. Now in the first example for these notes, we're looking at SAT scores and ACT scores. So we have 10 randomly selected scores on each test, and those are listed there. Then based on this data, we want to find out who scored better. The person with the 1829 on the SATs or the person with the 25.8 on the ACT. We want to support our answer with calculations and use statistical terms. Right, so just like in the introduction problem, I want to create a table of these values. So I'll have the SAT over here and the ACT over here. Right, now we need to use our calculator to get the mean and the standard deviation of each data set. So we need to do this twice on the calculator. With the SATs, we find that the mean is 1356.8 with a standard deviation of 346.52. And in the problem, we're looking specifically at the data value of 1829. So we can find the z-score of this. That will be the data value minus the mean divided by the standard deviation. So we have 1829 minus 1356.8, all divided by 346.52. This gives us a z-score of 1.36. On the ACT, using the calculator to find the mean and the standard deviation, we have a mean of 21.52, a standard deviation of 3.86, and the data value that we are looking at is 25.8. Right, so again, using the z-score formula, we have our data value minus the mean divided by the standard deviation. We have 25.8 minus 21.52, all divided by 3.86. We end up with a z-score of 1.11. So looking at these two z-scores, the score on the SAT is slightly above, is slightly further above the mean than the ACT score was. So we would say that an 1824 on the SATs is better than a 25.8 on the ACTs because it is further above the mean with a z-score of 1.36 compared to 1.11. Our second example takes a look at sales from two different electronics stores. So you work for Mike's TV and Repair and are happy that you sold 10 TVs today. Your friend works at Best Buy and say Best Buy had the better sales day because they sold 27 TVs today. So the sales data for the last 7 days is below. We want to determine which score had the better sales today. So we want to support our answer with calculations and again explain using statistical terms. So again, we need to use our graphing calculators to find the mean and the standard deviation of both data sets separately. So we have Mike's TV and Repair, and then we have Best Buy. At Mike's TV and Repair, using the calculator, we find that the mean is 8.14 and the standard deviation is 1.35. Right now I use my notation for sample mean and standard deviation because we only have 7 days worth of data. Right? That's not every single day that both stores have been open. Now, our data value that we're using for Mike's TV and Repair is 10 because they sold 10 TVs today. And we can find our z-score. Substituting 10 minus 8.14 divided by 1.35. Right, that gives us a z-score of 1.38. Right, so they sold more TVs than average, a little over one standard deviation. Still a usual amount of TVs that they sold. It wasn't an unusually good sales day. Right. At Best Buy, we find that their mean is 28.57. Right? Their standard deviation is 4.35, and their data value we are looking at is 27. Right, so we'll find the z-score of Best Buy selling 27 TVs in one day. We take 27 minus the mean of 28.57 divided by the standard deviation of 4.35, and we get a z-score of negative 0.36. Right, so even though Best Buy sold more TVs than Mike's TV and Repair, Best Buy still had a day that was less than average for them. So we could say that you had the better sales day at Mike's TV and Repair because you sold TVs at a rate of 1.38 standard deviations above the mean, while your friend at Best Buy sold a little less than the mean, so they sold less TVs than their average day.